Thanks very much to the organisers for asking me to summarise for you some recent results from the EDGE project. This is a project I've been involved with for some years now, which is looking at the interaction between the history of dwarf galaxies, the way they accrete material, especially in the early universe, which I'll come to the significance of that in a minute, the interaction between that and the feedback processes that kind of cause the self-regulation of those dwarf galaxies. Um, I guess I thought I would start just by explaining why dwarf galaxies are interesting objects to study. And since there's not much time, I'll just give you two reasons using a couple of examples from the literature. The first reason on the left there is understanding their abundance. And in particular, we now have good constraints on the abundance of dwarf galaxies that are satellites of the Milky Way. That allows us to get a handle on how many low mass objects there are orbiting the Milky Way, or hopefully in the future, also better constraints on how many of these low mass objects there are out in the field as well. And that in turn can be translated into a constraint on the small scale power in the cosmological power spectrum. And that in turn translates into a constraint on the particle physics of dark matter, because if you have a dark matter candidate that free streams in the early universe, so in this example, this is looking at sterile neutrino, warm dark matter specifically, the free streaming erases small scale structure and stops dwarf galaxies from forming. So this is a plot from Ethan Nadler and the DES collaboration using the abundance from the DES survey of Milky Way satellites to put constraints on how massive a sterile neutrino candidate for dark matter can be. And as you can see that as you add more and more data to this, so DES and pan-stars in this case, relative to just the SGSS dwarfs, you move to the right in here, you start ruling out larger and larger masses for a warm dark matter particle, and you start ruling out interesting areas of this phase space. So the abundance is interesting, but as well as that, the kinematics are interesting. That is the internal kinematics of dwarf galaxies. So the way that stars are orbiting around within the galaxies, or in many cases, gas is orbiting within the galaxies. This is a compilation of measurements put together by Justin Reed in 2019, taking a lot of dwarfs, again, around our Milky Way, and using kinematical information to figure out an estimate of the central dark matter density in those dwarf galaxies. And he's plotting it there as a function of stellar mass. And what you find is that there's quite a big diversity. So the central dark matter density in these things varies a great deal. There's an overall trend that as you go to higher stellar masses, you get lower dark matter densities. And this strongly contrasts with what you would expect in a purely cold dark matter universe where nothing interesting was going on, where you would more or less predict a fixed central density of dark matter. So this is something that's sometimes referred to as the cusp core issue, to do with how centrally concentrated the dark matter densities are in these dwarf galaxies. I should say there's a lot of discussion around how these observations work and how trustworthy they are, but I just don't have time to go into that. I just wanted to give this as a kind of two bits of motivation. Now, obviously, if you see these very different dark matter densities compared to predictions, you could interpret that as evidence for exotic particle physics within the dark sector. Or you could just say, well, it's telling us something about galaxy formation itself. And both of those remain possibilities at this point in time. So those are my two motivations, I guess, if I have to distill it down for why this project is even interesting. I've been working on a sort of broader project funded by the ERC for the last 6 years or so. We're just coming to the end of that project. It's called GM Galaxies. It's incorporated and worked with a very large number of people. But in terms of its results for dwarf galaxies, that's been within this sort of project called the Edge Project, which is a project that I set up alongside Oscar Agertz and Justin Reed some years ago. So it's kind of a combination of the genetically modified idea, which I'm going to tell you about in just one moment, with very high resolution simulations of these dwarf galaxies that I'm also going to tell you about. So just to give you the idea of what we mean by genetically modified galaxies, I'm going to show you an example that this is not actually dwarf galaxy. This is more like a Milky Way mass galaxy. And I'm going to very briefly show you some work from Nina Roth, who was a postdoc that worked with me many years ago on this. And we started working on that and have built on it ever since. And the essential idea is if you're going to perform high resolution cosmological simulations of galaxies, which is interesting for a variety of reasons, including the ones that I was just telling you about, then it's very useful to be able to tell what the final galaxy responds to in terms of its history, or to put it another way, in terms of the initial conditions in the early universe. So to cut a very long story short, at its heart, GM Galaxies is about performing simulations with pretty standard computer codes that are widely used to simulate galaxy formation. But instead of just simulating one galaxy at a time or a big box of galaxies, we have this sort of hybrid approach where we simulate one galaxy, but we then re-simulate it with controlled changes to its formation history. I don't have time to tell you exactly how we make those controlled changes. I'm always very happy to talk about that. But it essentially offers the possibility to see what the effect of particular moments in a galaxy's history are like. So here I've got an example. You can see there's these three panels. They are going to have a merger in this case that takes place at different times. You can see as I run time forward, the overall formation history and the cosmic web that this galaxy is forming out of is very similar in the three cases. But I've highlighted a particular merger that takes place that we changed the timing of that merger. We changed the way that this galaxy built up its mass while keeping other factors like the geometry of the cosmic web and the overall environment fixed. And then you can run those simulations forwards in time and see what the effect on the final galaxy is. Now, in this case, I'm going to be talking about dwarf galaxies, but I just wanted to mention in passing that at higher mass scales, we can do all sorts of interesting experiments here, like changing the merger strength of galaxies and seeing how that affects the morphology and the stellar streams and so on within galaxies, or changing the angular momentum of a galaxy. There are lots of different things that we've been doing within this project, but I'm focusing in here on the dwarf galaxy scale. So specifically for the dwarf galaxy scale, as I said, within this Edge collaboration, we've been using the Ramses code. It's an adaptive mesh refinement code, which allows us to simulate dwarf galaxies with roughly 3 parsec resolution in their interstellar medium. So this is really the highest resolution simulations in cosmological simulations of dwarf galaxies that are available right now. And what's nice about reaching that kind of resolution is you start to resolve the blast waves of supernovae. And it also allows us to put in important effects like the radiative transfer of ionizing photons from young stars. So here I'm showing the effect of all of that physics on the gas in a region that's collapsing to form a small dwarf galaxy. You're seeing it. This is a very high redshift. I've paused just before reionization is about to affect this region. So you can see that we formed a number of teeny tiny little galaxies there. You're looking at the gas density there. As reionization takes hold, then all of those really tiny things lose their gas. And even in the end, that big, well, it's not big, it's a dwarf galaxy in the center that also loses its gas. This corresponds to a kind of ultra faint galaxy in today's universe. It wasn't even able to hold on to its gas once reionization swept through and heated that up. Now, One of the things that we've been emphasizing throughout this project, and most recently in a paper that introduced a sort of second generation of these simulations, which my ex-PhD student Martin Ray authored, is that getting the physics at this resolution correct is absolutely vital. And one of the things that has really come out of this is that incorporating the radiative transfer of these ionizing photons from young stars is absolutely crucial. So here Martin is plotting as a function of stellar mass of a bunch of our different simulations, what is what's called sometimes called the mass loading factor of galactic outflows. So that's how much mass these things are losing to gas flowing out from the galaxies. You saw that in the animation a moment ago. That there's lots of outbursts which carry mass away from these galaxies. So what's that mass outflow rate divided by the star formation rate? So for a given solar mass of star formation, how much gas then gets expelled from the galaxy? You can see that if we just have supernova feedback in these galaxies, we lose an enormous amount of our gas because of the supernova explosions driving it out. Some of that later flows back in, but it is a very explosive kind of mechanism if you just have supernovae. If you add radiation feedback into your into the physics that you're tracking, then you find that these outflow rates are actually sort of an order of magnitude lower, which is a little strange at first because you're adding more energy. So you might imagine that that would enhance the outflow rates, but what it does is it adds the energy in a much more diffuse way. The ionizing photons go quite a long way from their parent stars, and they just gently heat the resolved interstellar medium in these simulations, which regulates star formation without actually needing to have these big outflows. And because star formation is therefore much less clustered, much less clumpy, the outflows that do come from the supernovae are much more distributed. And so you get this sort of much more gentle regulation of star formation, which is very important for stuff that I'm going to say in just a minute. In terms of direct observational implications of that, if you look at something like the metallicity of dwarf galaxies, then it shifts their metallicities upwards because you're essentially losing less of the enriched gas out into the intergalactic medium. You're retaining more of the enriched gas as time goes on. And broadly speaking, this is more consistent with observations. There are a lot of simulations out there that are being performed at the moment that predict extremely low metallicities for their dwarfs, essentially because they have very explosive feedback mechanisms that remove a lot of gas from dwarf galaxies. We feel that this is now ruled out because when you look at the metallicities of dwarf galaxies, they don't go down to the sort of 10 to the minus 4 of solar that some other simulations are predicting. So to come on to the sort of promised topic of how the interaction between these feedback mechanisms that I've been describing, how that interacts with history, I'm now going to rewind in time a little bit and talk about Martin's thesis work back in 2019. And sort of core focus of that was the way that reionization, and I'm now talking about cosmic reionization, which is powered largely by UV photons from sources that are not the dwarf galaxy itself. These are sources outside our notional box. So that this is UV photons coming in from the rest of the universe. And that happens around about redshift 6. The interaction with how the dwarf galaxy is building and accreting its mass with that overall process of reionization really makes big differences to the observed galaxy. So to test that, we used this genetically modified idea to make variants of a single galaxy which simply accrete their mass at a different time. They reach the same final mass at redshift 0 of about 10 to the 9 solar masses, but they change their mass that they have at redshift 6. And if you watch the evolution of these things side by side, then depending on exactly when you build up the mass relative to reionization, I think the one on the left builds it up rather faster. It has a much larger mass at the time of reionization, and I've paused at reionization at redshift 6 or so. Um, and so it's built up many more stars by the time reionization comes through. So if I carry on time now, then you'll see that because reionization then removes the gas from these objects, more or less, you're left with many more stars if you just happen to build up your mass earlier on. And so you can actually see this if we plot the stellar mass as a function of time at fixed overall dynamical or halo mass, you actually get a dex of scatter or so in the predicted stellar mass from these simulations, depending on exactly when they collapsed relative to reionization. Not just that, but when you look at the latest forming systems, they actually build up a large fraction of their stellar mass just from dry mergers that happen late on. So just you know, merging together a bunch of systems late on contributes a lot to the overall stellar mass, which means that not only if you plot this on a sort of brightness versus size plot, not only do those early collapses, not only are they brighter lying up here, they're also more concentrated. These late collapsing things are dimmer, but they're also actually very diffuse because they have built up a lot of their stellar mass through mergers. Now, I know I've got to stick to a very strict 18 minutes and I'm approaching the end of that. So I'm just going to mention very quickly that as you go to higher mass, then you can start to probe other types of physics. So this is now looking at something that is about 5 times more massive than the galaxy we were looking at before. And this becomes very interesting for understanding the processes that change the dark matter density within galaxies, something that I mentioned at the beginning. And my just finishing PhD student, Claudia Mooney, has been looking at this process. So earlier on, I pointed out that the dark matter density is, but first of all, declining as you go to brighter objects, but it's also got a lot of scatter. And she's been able to attribute that scatter essentially to variations in the formation history of these dwarf galaxies. But unfortunately, I've run out of time to describe that in detail, so I'll have to refer you to the paper or to the discussion session for a more detailed discussion of how all of that works. So right now, I will just skip to the summary and I will leave it at that.